All right, hey guys. So we're going to go over the study guide and look at everything. All right, so we'll start with chapter 12 and the true or false. So when two wires are close together with currents that run in the same direction, they're attracted to each other. That's true. And if they run in opposite directions, then they repel one another. The infinitesimal magnetic field created by an infinitesimal section of wire containing a current I is perpendicular to the direction that the current is traveling. If you look at the Biot-Savart law, then the infinitesimal magnetic field is mu naught over 4 pi I dl cross r hat. So that cross product means that it's perpendicular to both the direction of the current and the direction that points to where you want to know the magnetic field. So this next part, an ideal solenoid only has a magnetic field inside of it where it's constant, and it has a zero magnetic field outside of it. So some people have asked me about 4 and 5 because they seemingly contradict each other, but they don't. So Ampere's law says that this integral is equal to mu naught times the current enclosed. That is always true. It just is. This is always true 100% of the time. But you can only use this to actually solve for the magnetic field in cases of high symmetry. So in particular, if you have cylindrical symmetry. So if you have a long wire or you have a long thick wire, something like that, something that doesn't change along the direction of the cylinder, it only changes as you get farther from the cylinder, then you can use Ampere's law to actually solve for the magnetic field. So that's what 4 and 5 are saying. All right, you can always find the magnetic field from a long straight wire, or at least find the direction by using the right-hand rule. So if you put your thumb in the direction of the current, then your fingers curl in the direction of the magnetic field. So in the case of the first short answer here, it says that the current is coming out of the page. If you put your right thumb in that direction, then your fingers curl counterclockwise, which means that the magnetic field goes counterclockwise as well. Okay, so an ideal solenoid has 4,500 loops and is 0.25 meters long. It has this current, and the current runs clockwise as seen from above. What is the magnitude and direction of the magnetic field everywhere? So I've drawn it from above here. So the current is running clockwise. It's running like this. The magnetic field of a solenoid is, remember, only inside of the solenoid, and it's given by mu naught times the number of turns per meter times the current. So in our case, that would be mu naught times our 4,500 loops times the current divided by the length. And so that gives us the magnitude of the magnetic field, which, remember, is only inside the solenoid. Outside of it, the magnetic field is 0. And then we can find the direction once again by using the right-hand rule. So we say that our current runs clockwise as seen from above. So if you put your thumb, if you point it like in this clockwise direction, so that can be anywhere around on this circle, you'll see that your fingers point into the page. So that's the direction that the magnetic field is going. All right, so 3, an engineer wants to construct a floating countertop, which is not connected to anything, but just floats in the air. And she does this by using the magnetic force. So there's a 20 kilogram countertop that's placed on top of a 1 meter section of wire. And 2.5 meters below it, there's a second wire with the same length and the current running the same current, but running in the opposite direction. So from what we saw before, that means these wires repel each other, okay? So this top wire has 2 forces on it. It has the magnetic force that pushes up and the force of gravity from the countertop that's sitting on it that pushes down, okay? So since we want this wire to just float, it means that these forces have to be equal. Well, the force of magnetism on a current carrying wire is given by this thing. Normally, this would be the current in the first wire times the current in the second wire. But in our case, these currents are the same. So we just get I squared. And normally we solve for the force per unit length. So F over L would be equal to this stuff without the L. But this time we were given a link and we're just ignoring any boundary effects. In reality, this only works for really, really long wires or infinite wires. But if we just ignore the boundary effects, we can just multiply by the length. So this thing has to be equal to the weight of our countertop. We can solve for the current here just by isolating it. So we have this expression here. And then this R here is the distance between the wires. Well, we were told that was 2.5 meters. And then our length was 1 meter. And we know the mass and the mass of our countertop as well as the acceleration due to gravity. So we can plug everything in here and that gives us a current of 50,000 amps. Now that's huge and it should be. This force, this magnetic force on current carrying wires is very small and it increases as the distance between the wire increases. Okay, or it decreases as the distance increases. So these wires are so far apart, 2.5 meters, that we're going to need a truly insanely large current to be able to hold up such a heavy countertop. All right, so we want to find the value of this integral for this case. So remember, this is equal to mu naught times the current enclosed. In other words, the current that pierces the area that's defined by this loop. Okay, and so once again, we can use a right-hand rule. If we point our fingers in the direction that the loop curls around, so in this case, it curls around clockwise, we can see that our thumb points into the page, at least if you use your right hand, as you should. Your thumb points into the page. So that means that currents that go into the page are positive and currents that go out of the page are negative. So that's why I enclosed is +7 plus +5 minus 3. So that gives us 9 amps total. And so the integral is equal to mu naught times 9 amps. I mean, we could get a number for this if we wanted to, but why? Okay, so last short answer. A wire runs from north to south with a current running north, and an electron above the wire is traveling south. What is the direction of the force on the electron? So I've drawn that here with our coordinate system here. So this is north, this is south, into the page is west, out of the page is east, and down or up and down. All right, so we have our current that is running north. That creates a magnetic field. We can find the direction of it using the right-hand rule. So we point our thumb in the direction of the current, and we can see if our fingers are above the wire, then they point out of the page. So that's the direction of our magnetic field. Now our electron is traveling south. It's traveling this direction in a magnetic field that points out of the page, which is east. Okay. So if you remember to find the direction of the force on a charged particle, if it's positive, you use your right hand. If it's negative, you use your left hand. Well, electrons are negatively charged, so we'll use our left hand. We put our fingers in the direction of the velocity. So in this case, this is south, and we curl them in the direction of the magnetic field, which is east or out of the page, and our left thumb points down. So that's the direction of the force on the electron. Okay. So you have an infinite wire that runs along the x-axis with a current running in the positive x direction. And we want to find the magnetic field some height y above the wire. So I initially put r here, but then there were too many r's and things got confusing. All right, so we can draw our setup here. This is the x direction, this is the y direction, and out of the page is z. And so we want to know the magnetic field up here, where this distance is y, okay? Well, the Biot-Savart law tells us this thing. And the magnetic field given by a current carrying wire is this, where we integrate over the wire itself. So we need two things. We need dl. Remember, dl points along the direction of the current. In our case, the current is going in the positive x direction. So dl points in the x direction. And it's also the length of a little piece of the wire here. Well, since the wire is along the x-axis, it's just dx. And like I said, it points in the I hat direction. Now our R vector, that's the vector that points from an arbitrary DL to where we want to know the magnetic field. So to get from here to here, if we call this point where we want to know it x equals 0, that means that this distance is x. And so to get from here to up here, we have to go negative x in the x direction and positive y in the y direction, which is exactly what I've written here. Now, what we really want is the unit vector. So the unit vector is the vector divided by the magnitude. And the magnitude of this vector is just the square root of x squared plus y squared. Okay. So if we plug all that stuff in, we can pull the current out because it's just some number. And so we get dx I hat cross this thing. And then on the bottom here, we have this x squared plus y squared to the 3/2. So in the equation, this is squared, and little r is just the square root of x squared plus y squared. So this would be x squared plus y squared to the first power, but there's another half that comes from the r hat. So that's how we got this to the 3/2. All right, so now we have an I hat cross I hat term. Well, anything cross itself is 0. And we also have this I hat cross j hat term. Well, we can use the right hand rule. If we put our fingers of our right hand in the direction of x and we curl them in the direction of y, then our thumb points out of the page, which is the z direction. Okay. So if we put that all together, then we need to perform this integration. Okay. This k hat here came from our cross product. It just comes along for the ride. It doesn't really do anything. All right, now I would give you this integral. I don't expect you to be able to do this by yourself, but it turns out that the answer is this thing. And because our wire is infinite, we have to go from minus infinity to positive infinity. Okay. And if you do that, if you take those limits, then you end up getting this thing. So at this height y above the wire, our magnetic field is mu naught I over 2 pi y, and it's in the positive z direction. So in other words, that's coming out of the page. And that's the same direction that we would expect from the right-hand rule. If we put our thumb along the positive x direction, since that's the direction of the current, then when we're above the wire, our fingers point out of the page. All right, now we need to do the same thing using Ampere's law. Now, because we have cylindrical symmetry here, that means we can use Ampere's law to actually find the magnetic field. And this is going to be a million times easier than integrating. And so this says if we integrate the magnetic field over some closed loop, that has to be equal to mu naught times the current enclosed. It's the current that pierces the area here. And so if we use a circle of radius little r, where the wire goes through the center of the circle, that means we have a whole bunch of symmetry. That means our magnetic field can pop out of this, okay? And we'll also choose the direction for this loop to go around in the direction that the right-hand rule tells us. So if we point our thumb in the direction of the current, our fingers curl around. So this part behind the wire needs to be going up, and this part in front of the wire needs to be going down. And so if that's the case, our magnetic field and our DL vector point in the same direction, so we can get rid of the dot product. And then, like I said, because we have cylindrical symmetry, and so does our circle here, we can pull the magnetic field out. So this integral is just asking us what the length of this loop is. Well, it's a circle of radius r, so it has length 2 pi r. So 2 pi r times the magnitude of the magnetic field has to equal mu naught times the current enclosed. Well, the current that pierces this area is just I. So it's just mu naught times I. So if we solve for the magnetic field, we get mu naught I over 2 pi r, which is the same as the expression that we had up here. Now we're using r instead of y, but otherwise they're exactly the same. So if you were just given this problem, I said find the magnetic field due to a long or due to an infinite wire, Ampere's law is definitely going to be the way to go. This is much simpler than having to integrate over this wire. All right, let's go back up. Go right down. All right, so our second question here says to find the magnetic field at the center of a circular loop of wire of radius r and current I. All right, so that's what we're doing here to find a coordinate system where this is x, this is y, out of the page is z. And so we have a loop of wire here of radius capital R, and it has current I. Now we weren't told which direction the current was going in, so I just arbitrarily picked counterclockwise. Okay, so our DL, once again, is going to, so by the way, we do not have cylindrical symmetry here. So the only way that we can find this magnetic field is through the Biot-Savart law. And so we need DL, and we need R hat, and we need R. So DL points along this wire in the direction of the current. So I drew the direction of the current to be counterclockwise. So that's the phi hat direction. And the length of a little piece of circle here is always the radius times d phi. Okay, so this is how we find DL. And now we need the R vector that points from an arbitrary DL to where we want to know the magnetic field. Well, we want to know the magnetic field in the center of the loop. So that means we have to go some distance capital R and then toward the center of the circle. Well, R hat prime is radially outward. So minus R hat prime is radially inward. So we have to go radially inward a distance of the radius. Okay. And so if we took the, if we just wanted the unit vector of this thing, we would divide by the magnitude, which is just R. So our R hat, this should be minus R hat prime, sorry. All right, so the unit vector that points toward the magnetic, where we want to know the magnetic field, is this radially inward direction. All right, so if we plug all this stuff in, once again, this should be primed. Phi hat cross minus R hat is the Z direction. So we can see that just from the right-hand rule. So if we point our fingers along the direction of the circle, anywhere around the circle, and then we curl our fingers toward the center of the circle, then our thumb points out of the page. So that's in the Z hat direction. All right, so once again, this thing is just gonna stick with us. Okay. And also one of these R's is gonna cancel. And so we're just left with d phi over R. And we need to integrate from 0 to 2 pi because it's a full circle. If it had only been half of a circle, then we'd go from 0 to pi. If it had been a fourth of a circle, we'd go from 0 to 2 pi, whatever, etc. Okay, now notice nothing here actually depends on phi. So this integral is super easy, it just gives us 2 pi. So that tells us that our magnetic field is in the Z direction, and it has a magnitude of mu naught I over 2 times the radius of our circle. All right, so one more. We want to find the magnetic field of this wire that has a current density that's given by this thing. So this is a thick wire. It has a thickness to it. And so if little r is less than R1, then there's no current. If little r is greater than R2, then there's also no current. So in other words, we have a situation like this. So inside this middle circle, this middle cylinder, there's no current at all. There's only current in between the little circle and the big circle. And this makes an infinite cylinder. Okay, and we want to know the magnetic field everywhere. Well, there's 3 regions here. There's the region inside of the small circle. There's the region that's in between, and then there's the region that's outside of this. And because this thing is infinite, we actually do have cylindrical symmetry, which means that we can use Ampere's law. So we'll have to use a different Amperian loop in each of these 3 positions. So one inside the smaller circle, one in between, and one outside. Okay. Now Ampere's law tells us this integral over the magnetic field has to be equal to mu naught times the current enclosed. Well, if we use a loop inside of the small circle, there's no current there. We said nothing's going on there. So the current enclosed is 0. And because we have cylindrical symmetry, this integral is just going to be the magnitude of the magnetic field times the length of our loop. So that's 2 pi r times b. But this thing has to be equal to 0 because there's no current enclosed, which tells us that our magnetic field is 0 as long as we're inside the smaller circle. All right, our second region is in between them. So we'll take our Amperian loop to be in between them. And we'll take it to be of radius lowercase r. And so we do effectively the same thing. Because of the symmetry here, this integral is just the length of our loop, which is 2 pi r, times the magnitude of the magnetic field. And this is equal to mu naught times the current enclosed. Well, the current enclosed is all of the current that pierces through this area. Well, we don't know the current, but we do know the current density. That's what was told to us in the problem. It was A over R as long as we're in between R1 and R2. And so we have to integrate this over the area, and that will tell us our enclosed current. So anytime we integrate over a circle, the unit area is R dr d phi. So we've done that, we've seen this several times now. And so this R is going to cancel with this R, and this A is just a number, so it can be pulled out. And we only want the current that's enclosed in our Amperian loop here. So that goes from R1, because that's where the current starts, up to lowercase r, because that's all the current that we care about. And then it's still a full circle, so we still integrate from 0 to 2 pi. So that gives us an enclosed current of this thing. So we can set this equal to our I enclosed up here and solve for the magnetic field. And we get this expression. Remember, this is only true if R, lowercase r, is in between R1 and R2. Now, our third region is actually outside of the wire altogether. So this is where R is greater than R2. And so our Amperian loop is also drawn to be bigger than this. So we do the exact same thing that we did before. This integral is going to be the length of our loop times b. And that's equal to mu naught times the current enclosed. So once again, to find the current enclosed, we integrate our current density over the area like this. And this time we go from R1 to R2 because that's where all the current is. There's no current in between R2 and lowercase r, so we don't have to integrate over that part. So that if we actually perform this integration, this gives us a current of this. We can plug that into our Ampere's law and solve for the magnetic field, and we get this. All right, so that's this chapter. So the next chapter, electromagnetic induction. Sorry, I actually just realized that I left mu naught out of these. So both of these should have a mu naught in front of them. It's mu naught times that. So, okay, so chapter 13, electromagnetic induction. So the EMF that's induced around the loop does not care about the magnetic flux. It cares about the derivative of the magnetic flux with respect to time. So only if it's changing is there going to be an EMF induced. Not if it's constant. It doesn't matter what the size of it is, only how quickly it's changing. Okay, so Lenz's law dictates the direction of the induced EMF. That's true. And it always opposes a change in the flux. So if there's more flux coming through, it'll try to make its own flux that goes the opposite way. If there's less flux coming through, it'll try to make its own flux in the same direction. All right, the induced magnetic field created by the induced current in a loop of wire always opposes the external magnetic field. That is not true. It opposes the change in flux. It can either point along with or against the external magnetic field, depending on if the flux is increasing or decreasing. All right, now a loop of wire rotating in a constant magnetic field produces alternating current. So if you remember, we did the calculation, it was proportional to sine of omega t, where omega was the rate at which the thing was rotating. This is also exactly how an electric generator works, and those create alternating current. So in addition to an EMF, a changing flux through an area also induces an electric field. That's true. That's just another way of stating Faraday's law. Because there's an EMF, that means there's something that actually pushes the electrons around, and that thing is the induced electric field. Now, the units for flux, for magnetic flux, are Teslas times meters squared, which is what we define to be a Weber. All right, short answer. So a circular loop of wire is in the plane of the page with a magnetic field that points out of the page and is increasing. So in black here, I've drawn the external magnetic field, and it's increasing. So if it's increasing and the area and the angle are staying the same, that means the flux is also increasing. So there's more flux coming out of the page, and our loop doesn't want there to be more flux. So it creates its own magnetic field, its own flux that points in the opposite direction. So our induced magnetic field points into the page. Now we can figure out the direction of the current from the right-hand rule. There's only two possibilities. Either the current goes clockwise or it goes counterclockwise. You can try both of them and see what direction makes your fingers point into the page. In this case, our current has to go around like this. So if you take your right thumb and you put it like that, anywhere around this circle, when the current is going around like this, then your fingers will point into the page. All right, so a circular loop of wires in the plane of the page with a magnetic field that points out of the page and is decreasing. So our magnetic field points in the same direction, but it's decreasing this time. That means our flux is also decreasing. Well, our loop doesn't want the flux to be decreasing. So it creates its own magnetic field that reinforces the external one. So it points in the same direction. And once again, we can find the current via the right-hand rule. So notice if you point your thumb counterclockwise anywhere around this loop, then the fingers of your right hand will point out of the page, which is in the direction of the induced magnetic field. All right, so one more like this. All right, so a circular loop of wire in the plane of the page has a radius that's given by alpha times t, and it is in a constant magnetic field that points out of the page, and the whole loop has a resistance R. So what is the direction of the induced current and the induced magnetic field? And write an expression for the current as a function of time. So this time, our magnetic field is constant, but our area is increasing. So as it gets bigger and bigger, it lets more and more flux into the loop. So because the area is increasing, that means the flux is also increasing. So there's more flux coming out of the loop. It doesn't like that, so it creates its own magnetic field that opposes that flux. And so if we do the same thing that we did in one, we'll see that the current has to go around like this. So clockwise, yes, clockwise. All right, so the EMF, or at least the absolute value of the EMF, is given by the derivative of the flux. In this case, our magnetic field is constant, and it points along the normal. Remember, the normal is the vector that's perpendicular to this area. So in our case, it's either out of the page or into the page. And we always choose the one that has the smallest angle with the magnetic field, with the external magnetic field. So that means our normal points out of the page. And so our flux is just the magnetic field times the area. So the magnetic field is just some number B, and our area is pi r squared, but r is given by alpha t. So our flux then is B times pi alpha squared t squared. And our EMF is the time derivative of this thing. So we pick up a 2 and the t drops to the first power. This is our EMF. And if we want the current, we just divide that by the resistance of our wire here. So this is our current as a function of time, and it goes clockwise around the loop. All right. So this is for that problem. This is for this problem. So the picture shows a magnetic field that points into the page and is decreasing with time. Which of these curves has this integral over the induced electric field not equal to 0? Well, Faraday's law says that this integral over any loop is equal to minus the change in the magnetic flux through the loop. Okay, So if this magnetic field was constant, if it wasn't changing, then the integral of the electric field over all of these loops would be 0. Okay, but that's not the problem we have here. We said that our magnetic field here is decreasing. So because it's changing, any loop that has part of this changing magnetic field in it is going to have this integral not equal to 0. So that's P1 won't have it equal to 0 because there's a little bit of the magnetic field going through here. P2 will have it not equal to 0 because inside of P2 is this changing magnetic field. The same for P4. Only P3 actually has it equal to 0. And that's because none of the magnetic field lines are traveling through this P3 here. Okay. So our next one. A coil of wire with 4 loops has a radius of 10 centimeters and a resistance of 10 ohms and surrounds a long solenoid with 1,250 loops per meter. And it has a radius of 2 centimeters. If the current in the solenoid uniformly changes its current from 0 amps to 1.5 amp, find the induced EMF and the current. And I left this out, but I added it later, that it does this in 10 seconds. Okay. So we have our big loop and it surrounds a solenoid here. And so the solenoid only has a magnetic field that comes through the middle. There's nothing on the outside and it points along the solenoid, depending on the direction of the current. And so our flux is just our magnetic field times our area here. So the magnetic field of a solenoid is mu naught times the number of turns per meter times the current. And the area is pi r squared, and we'll use the area of the solenoid, not of this big loop. And the reason why we do that is because there's only a magnetic field inside the solenoid. So all the space out here has no magnetic field in it. All right, so that gives us a flux of this thing times the current, okay? We weren't given a current, or we were only given the change in the current, not the current itself. Okay, now our EMF is given by the number of loops times the derivative of this thing. And so this thing is just the number of loops in our outer one, which we said was 4, times the derivative of the flux. Well, this is just a number, so that comes out of the derivative. So we have this number times the change in the current. Now, because our current changes uniformly, and only because it changes uniformly, the derivative is the same as the finite difference. So we can subtract the final current from the initial current and divide that by the amount of time it took for that to happen. So we have 4 loops, multiply by this number, and the change in the current, it went from 0 to 1.5, so that's 1.5 minus 0, and it did it in 10 seconds, so we divide by 10. So that gives us an EMF of 1.18 times 10 to the minus 6 volts. And to find the current, we just divide by the resistance, which we were told was 10 ohms. So that gives us a current of 1.18 times 10 to the minus 7 amps. All right, so we have one more. This is a motional EMF problem. So this current, the circuit here is stuck in place, but this PQ portion of the wire is free to slide. So it can slide wherever it wants to, but we were told it's sliding this way at a constant velocity of 2.5 centimeters per second. And our whole circuit has a resistance of 100 ohms. Now, in reality, as this thing slides, the resistance would change, but we're just ignoring that, okay? And it's in a constant magnetic field that has a magnitude of 735 microtesla. Okay, and what are we looking for? We're looking for the current, the direction of the current, and the magnitude of the applied force. All right, well, our EMF in this case is given by the magnetic field times the length of the sliding wire times its velocity. And to find the current, we divide that by the resistance. So our current is BLV divided by the resistance. So this gives us a numerical value of 1.8 times 10 to the minus 8 amps, but it doesn't tell us the direction. So we'll have to use Lenz's law to find the direction. So as this thing moves this way in a constant magnetic field, that tells us that there's less and less flux as it moves over because the area is decreasing. Okay, so that means it creates its own magnetic field to reinforce that external one. So it also points into the page, just like the external magnetic field does. So if we use the right-hand rule, we can see that our current has to go around like this, so clockwise, in order to produce a magnetic field that points into the page. So in our bar here, that means the current is moving down. So our answer is 1.8 times 10 to the minus 8 amps down. Now we also want to know about the applied force. Okay, well, there's a current that goes through this wire now. And because there's a current in a magnetic field, that means there's a force on it. And we could either use the right-hand rule to figure out that the force has to be to the right, or we could just remember that it always opposes motion. Okay, so this magnetic force is always going to oppose the direction that this thing is moving. So if it had been moving out this way, then the magnetic force would be going the opposite way. All right, now since it's moving at a constant velocity, that means there must be an applied force that counteracts this magnetic force. So it has to go in the opposite direction, but they have to have the same amplitude, or the same magnitude rather. All right, now the magnetic force, at least if the current is perpendicular to the magnetic field, as it is in this case, is just the current times the length times the magnetic field. Well, we already found the current. We were given the length of this wire and the magnetic field. And so this gives us a magnetic force of 1.3 times 10 to the minus 12 newtons. But our applied force has to have the same magnitude and in the opposite direction. So our applied force is 1.3 times 10 to the minus 12 newtons, and it's directed left. So the applied force always has to go with the velocity. The magnetic force always opposes the velocity. All right, so long answer. Let's see. Oh, okay, yeah. So the only question I could ask you is to actually find the magnitude of the induced electric field here. And so we'll use Faraday's law, which says that if we integrate the electric field over some closed loop, this has to be minus the change in flux, or the rate of change of flux, of magnetic flux. So we have to do, this is very similar to what we do with Ampere's law. We have to draw an Amperian loop, and there's two different regions. There's one region that's inside of this solenoid, and there's one region that's outside of the solenoid. And we were told that the current in the solenoid is exponentially decreasing. Okay. All right. So because of our symmetry here, we have a solenoid. So we have cylindrical symmetry. That means that our E.dl here, first off, we can ignore the direction because we chose it to go in the direction that the electric field is going. Then the electric field pops out of the integral. So this is just the length of our curve, just 2 pi r, times the magnitude of the electric field. This is equal to minus the derivative of the flux. Okay. Well, the flux just goes straight through this loop. There's no angle, and the magnetic field of the solenoid is constant. So that means it's just the magnetic field times the area. And the area of what? The area of this Amperian loop. That's the only thing that we care about the flux through. Okay. So our magnetic field of a solenoid is mu naught times the number of coils per length times the current, and then times the area of our loop. All right. And so that gives us this thing. All of these things are constants. They don't change with time except for the current. So we're left with the derivative of this current. And we were given our current as a function of time. So when we differentiate this, we'll pull out a minus alpha. So the minus will cancel with this minus, and we have an extra alpha here. Okay. And so when we set these things equal, this equal to this, we can solve for the electric field by dividing by 2 pi r. And so one of the r's will cancel, and we'll end up with a 2 in the bottom, and the pi will cancel as well. So this is the electric field if we're looking at a distance of less than the radius of the solenoid. If we want more than the radius of the solenoid, we'll have to draw another Amperian loop, also of radius r, but this time bigger than the solenoid. Okay. And so we do the same thing again. This integral is going to be the length of our Amperian loop times the magnitude of the electric field. Our flux is still B times A, but this time the area is only the area of the solenoid. There's no magnetic field in between the solenoid and the loop. The magnetic field of a solenoid is only inside the solenoid. So we only have to worry about that area. So that's the area that we put here. Once again, all of these things are numbers except for the current itself. That's the only thing that changes with time. That's the only thing you have to differentiate. And so once again, you'll end up with something like this. The only difference between this and our last expression is that we have capital R here instead of lowercase r. But if we set this equal to this, we divide by 2 pi r, and this is our electric field if our radius is larger than the radius of the solenoid. All right, so that tells us the electric field everywhere, and that wraps up that chapter. All right, so next chapter, inductance. So mutual inductance, we talked about this, only depends on the geometry. So the mutual inductance is how different circuits induce EMFs in each other. And the only thing that matters is how they're aligned relative to each other, how many loops they have, that kind of thing. So it only depends on geometry, not on the current. Any dependence on the current divides out. All right, now inductors do store energy, but they do it in magnetic fields, not in electric fields. So capacitors store energy in electric fields, and inductors are sort of like the magnetic version of capacitors. Okay, so when a DC circuit that consists of just a battery with EMF epsilon and a resistor with resistance R are connected in series, its current discontinuously changes from 0 to the EMF divided by the resistance. This is false because of the self-inductance in the circuit. When the current first starts going, that creates a magnetic field. So that magnetic field creates a changing flux through the loop. And so that induces an EMF that opposes the EMF of the battery. And so because of that, it takes a little while for the current to reach up to its maximum value. It definitely doesn't just jump up to it instantly. All right. So when a charged capacitor is connected in series with an inductor, the current in the circuit exponentially decays. No, that is not true. So we looked at this and we saw that the current is sinusoidal. So sometimes it's really big going in one direction, sometimes it's really big going in the other direction, and sometimes it's 0. So this happens as energy is transferred between the capacitor and the inductor. So if the capacitor is charged initially, all of the energy is in the electric field of the capacitor. And then that charge that's on the plate starts leaking out, and that creates a current. And eventually, when all the charge is gone from the capacitor, the current is at its maximum value and all of the energy is in the inductor, and then it goes the other way. All right, so finally, self-inductance always produces an EMF that opposes the current in the inductor. That's false. It opposes change in the current. So if the current is increasing, then it will oppose that current. But if the current is decreasing, then it will reinforce that current. All right, so for the short answer questions. All right, so a solenoid functions as an inductor. It has a length of 10 centimeters, 400 loops, and a radius of 0.5 centimeters. If there's a current passing through the solenoid, which is changing at a rate of 10 amps per second, what is the induced EMF in the inductor? Well, the induced EMF in inductor is always minus the self-inductance times the rate of change of the current. We weren't given the self-inductance, but we do have a formula for it as long as it's a solenoid. So if it's a solenoid, it's mu naught times the total number of loops squared times the area of each loop divided by the length. So these are things that we know all of. There's 400 loops. The length was 10 centimeters. And the area, it's the area of a circle, is pi r squared. So it's pi times the radius squared. Sorry, my dog was mad at something. So if we perform that calculation, that gives us 1.6 times 10 to the minus 4 henries. Remember, that's what inductance is measured in. And so most of the time we don't actually care about the sign of the EMF, so we can just take the absolute value. And so we multiply this inductance, self-inductance, by the rate at which the current is changing. And that was given to us in the problem. So we take our 1.6 times 10 to the minus 4 henries, we multiply it by our 10 amps per second, and that gives us the EMF induced in the solenoid. All right, so the next one says to rework the problem that we worked before, where we had the 4 loops that had a solenoid inside of it, but this time working it using mutual inductance. So mutual inductance is given by either the number of loops in one times the flux through that one due to the other divided by the current in the other one, or vice versa. You can define it either way. From symmetry, you'll get the same thing. But in our case, it'll be much easier to find the flux through the outer solenoid rather than the inner one. Okay, so we'll use the flux through the outer one due to the inner one, which is the magnetic field due to the inner solenoid, which is this, times the area of the inner solenoid. And we divide that by the current, and so the current divides out. And so we're just left with these geometrical quantities that we were already told in the problem. So that gives us the mutual inductance. And then the EMF is this mutual inductance times the rate of change of the current. So once again, we were given this, that it changed from 0 to 1.5 in 10 seconds. And because it changed uniformly, this finite difference is the same as this derivative. So we just multiply that by our mutual inductance, and that gives us our voltage, our EMF. All right, so an RL circuit consists of a battery with an EMF of 10 volts, an inductor with a self-inductance of 145 millihenries, and a resistor with a resistance of 225 ohms. The circuit is connected at t equals 0. Find the time at which the current is half of its maximum value. Then we also want to know how much energy is stored in the inductor at this time and what percentage this is of the maximum energy. So our circuit looks like this. We have our battery, we have our inductor, and we have our resistor. Now, the formula for the current in this circuit is given by this thing. It's the EMF of the battery divided by the resistance times 1 minus e to the minus t over tau. Okay, so as time goes on, this part goes to 0, and it gets closer and closer and closer to the EMF divided by the resistance, which is what the current would be if the inductor weren't there. So the inductor just slows down this current. It prevents it from immediately reaching this value. And so we want this thing to be half of its value, half of its maximum value. Well, this number here is its maximum value. So we just stick a 0.5 in front of it. And so this is the equation that we want to solve for t, okay? Well, notice that the epsilon over r can just divide away. Then we can isolate the exponential, and we'll be left with this thing. And then we just take the log and solve for t. So t is minus tau times the log of 0.5. And remember, tau is the time constant for an RL circuit, and it's given by the self-inductance of the inductor divided by the resistance. Well, those are things that are given in the problem. And so we can solve for time. Whoops. We can solve for time, and we get 4.5 times 10 to the minus 4 seconds. Okay. Now, we want to know the energy at this time. And so the energy in an inductor is given by 1/2 the self-inductance times the current squared. So before we can calculate this, we need to know the current. And so we can either just plug in the time that we just found into our formula here, or we can use the fact that it's half of its maximum value. And so that's 0.5 times the EMF of our battery divided by the resistance. So that gives us a current of 0.022 amps. So we plug that into our equation here, and it tells us that at this point in time, we have 3.5 times 10 to the minus 5 joules worth of energy. So to find the percentage this is of the maximum energy, we divide this energy by the maximum energy and multiply by 100. So our energy now is this thing. And for our maximum energy, we use the same formula, but we use our maximum current. So our maximum current is the EMF of our battery divided by our resistance. And so we plug this in, we get 25%. So even though we're at half of our current, we're only at 25% of our maximum energy stored in our inductor. That's also exactly what we would think because this thing is squared. So if we plugged in half of I max squared here, the half will get squared and we'll go to a fourth. All right, so one more for this chapter. An LC circuit consists of an inductor with an inductance of 0.45 henries and a capacitor with a capacitance of 200 microfarads. The capacitor has an initial charge of 370 microcoulombs. So find the maximum current in the circuit and write expressions for the charge on each plate of the capacitor and the current in the circuit. All right, so first off, if you remember, we derived a whole bunch of equations for these LC circuits. And one of them said that the angular frequency of the circuit is given by the square root of 1 over the self-inductance times the capacitance. So these are things that are given in the problem. So if you plug this in, our angular frequency is 105 radians per second. Now our maximum current is given by our angular velocity times our maximum charge. Whatever the thing was charged with initially will be our maximum charge. So we just multiply our 105 radians per second times our 370 microcoulombs. That gives us a maximum current of 0.039 amps. Okay. Now, the charge as a function of time always looks like the maximum charge times cosine of omega times t. At least that's what it looks like if the capacitor starts off initially charged, and that's the only case that we're considering. If it started off not maximally charged or there was already some current, then you would have an angle that you'd have to add here, but we won't worry about that. So this is always what the charge is going to look like. And our current is always minus the maximum current times sine. So why is that? It's because the current is always the derivative, the time derivative of this thing. So if you differentiate sine, you get negative cosine and you pull an omega out. That's why the maximum current is omega times the maximum charge. And that's where this minus comes from. Now, the only other thing I could ask is something about the energy. So if you remember in an LC circuit, the energy is always changing from the energy in the capacitor, or specifically in the electric field of the capacitor, to the magnetic field in the inductor. So whenever the capacitor is maximally charged, all of the energy is in the electric field. And whenever the current is at maximum, all of the energy is in the magnetic field of the inductor. So it just keeps switching back and forth between those things, which means that the maximum energy can either be given by half the maximum charge squared over the capacitance. This is the formula for the energy in a capacitor. Or it's half the self-inductance times the maximum current squared. And if you looked at some point in between where the capacitor is not maximally charged, so you do have a current, but it's not the maximum current, then you'd have some combination of energy in the capacitor and in the inductor. All right, 2 chapters left. So alternating current. So the voltage through a resistor in an AC circuit is always in phase with the current. It's the capacitor and an inductor that have out of phase currents. And so our out of phase voltages, they're always either plus or minus pi over 2 out of phase with the current. So it is not typical to use the average current or voltage in an AC circuit because those averages are both 0. So instead, we use the RMS, our root mean square versions of the current or the voltage. Just a slightly different way of taking the average, where you divide the maximum value by the square root of 2. All right, so in an AC circuit with only a power source and a capacitor, the capacitor has a quality known as capacitive reactance, which tries to prevent the flow of current. That is true. Even if you don't have a resistor, if you have 0 resistance in your circuit, if you have just a capacitor or just an inductor, you still have a finite current, which means there must be something that's acting like a resistance. So for capacitor, it's capacitive reactance. And for an inductor, it's inductive reactance. All right, so on average, only capacitors and inductors contribute to the power in an AC circuit. That is not true. On average, capacitors and inductors do not contribute, but resistors do. Okay, impedance is measured in ohms. That's true. So remember, impedance is sort of like a generalization of resistance. Whenever you have resistors and possibly capacitors and inductors. And so if you add all of their contributions up in a special way, take the square root of the squares, then that's called impedance. And it acts just like resistance, so it is measured in ohms. All right, so unlike the resistance of a typical resistor, the inductive reactance of an inductor depends on the frequency of the power source. That is true. So does the capacitive reactance too. They both depend on the frequency, how quickly you change the current back and forth from going one way to going the other way. All right, so short answer. In an AC circuit, an AC circuit has a power source and a resistor with a resistance of 50 ohms and they're in series. If the voltage across the power source is given by this, so it's the maximum voltage times the sine of the angular frequency times time, then what is the current in the circuit? All right, well, we only have a resistor here, which means that the current is in phase with the voltage. So there's no phase angle here, which means that our current is given by our maximum current times sine of the angular frequency times time. Well, if by looking at this voltage here, you can see that 6 volts is our maximum voltage and 120 pi radians per second is our angular frequency. So we can just plug the angular frequency in right away, but we need to find the maximum current. Well, the maximum current obeys Ohm's law. So it's always the maximum voltage divided by the resistance. We said our maximum voltage was 6 volts and our resistance was 50 ohms. So that gives us a maximum current of 0.12 amps. So that's what goes in front here. All right, what are the maximum and RMS values for the voltage and current in the above circuit? To find the RMS values, we just divide by the square root of 2. Okay, so you divide the maximum value by the square root of 2. So the VRMS is the Vmax, which we said was 6, divided by square root of 2, which is about 4.2. And the IRMS is the Imax divided by the square root of 2. So that's 0.12 over the square root of 2, which is about 0.085. So I skipped this part by accident, but how much power is dissipated on average? The average power in a circuit with only a resistor is just VRMS times IRMS. So in this case, it would be our 4.2 times our 0.085. And power, as always, is measured in watts. All right, so an AC circuit has a power source and a capacitor with a capacitance of 120 microfarads. If the current in the circuit is given by this thing, then what is the voltage across the capacitor? All right, so our current is always our maximum current times the sine of our angular frequency times time. So that means 50 pi radians per second has to be our angular frequency, and 1.5 amps has to be our maximum current. So our maximum voltage also obeys Ohm's law, but we have no resistor here. So instead of the resistance, we have to use our capacitive reactance. So capacitive reactance is given by 1 over the angular frequency times the capacitance. And so that's our 50 pi radians per second times our 120 microfarads. So this gives us a capacitive reactance of 53 ohms. Okay, so if we plug this in here, this tells us that our maximum voltage is 80 volts. So our voltage is our maximum voltage times the sine of the angular frequency times time. And this time we have a capacitor and not a resistor. The voltage of a capacitor always lags behind the current by pi over 2. That means we have to subtract this by pi over 2. Okay, so for capacitors, it's always minus pi over 2. For inductors, it's always plus pi over 2. And for resistors, it's always 0. So what's the phase angle? The phase angle is just the angle that you have to add to the voltage after the angular frequency times time. So in our case, it's minus pi over 2. If we had a capacitor and a resistor, or possibly an inductor as well, that's going to shift this away from pi over 2, and it can be any value. All right, so we only have one long answer question from this section. And it says an AC circuit has a capacitor with capacitance of 45 microfarads, an inductor with an inductance of 130 millihenries, and a resistor with a resistance of 87 ohms. And we have an AC power source, and those are all in series. The RMS value of the current in the circuit is 500 milliamps, and the frequency, not the angular frequency, is 80 hertz. So to find the angular frequency, we just have to multiply by 2 pi. All right, so first we want the impedance. So the impedance is given by the square root of the resistance squared plus the difference in the inductance, and the inductive and capacitive reactances squared, okay? The inductive reactance is given by the inductance times the angular frequency, and the capacitive reactance is given by 1 over the capacitance times the angular frequency, okay? So we know all of these things here. The angular frequency is just 2 pi times the regular frequency, and the inductance and capacitance were given in the problem, as was the resistance. So if we calculate this, we have a total impedance of 90 ohms. All right, so now what are the maximum voltage and current in the circuit? Well, we know the RMS current was 500 milliamps, and the maximum is the square root of 2 times the RMS current. So in other words, it's the square root of 2 times 0.5 amps. So that gives us 0.71 amps. And the maximum voltage and the maximum current obey Ohm's law with the impedance, okay? So we can find the maximum voltage by taking our maximum current and multiplying by our impedance of 90 ohms. And so that gives us a maximum voltage of 64 volts. All right, now what is the phase angle? So generally, we can always find the phase angle like this. It's the arctan of the inductive reactance minus the capacitive reactance divided by the resistance. And so in our case, this is 0.24 radians. All right, now what is the average power dissipated? Well, if we only had a resistor, we wouldn't need this cosine part here because the phase angle for a resistor is 0. But because we do have these other parts, we have a capacitor and we have an inductor, we have to add, it's the RMS current times the RMS voltage times the cosine of the phase angle, okay? Now the RMS current is the maximum current divided by the square root of 2. The RMS voltage is the maximum voltage divided by the square root of 2. So this is the same as half, there's a square root of 2 from each of these, which multiply to be 2, times the maximum current, the maximum voltage times the cosine of our phase angle here. So we found these things up here. So it goes in here, and our phase angle is 0.24 radians. That's what goes in here. So that gives us a total average power of 22 watts. All right, now finally, write down expressions for the current and voltage as functions of time, assuming the current is 0 amps at 0 seconds and increasing. So all that means is that the current is given by the maximum current times sine of omega t. In general, you could have the phase angle attached to the current, but when we looked at it, we always attach it to the voltage, and I won't mix that up on the test, so it's always going to be like this. So we'll always assume that the current is just a bare sine, and then the voltage is the maximum voltage times the sine of omega t plus the phase angle, okay? And so we know what the angular frequency is. We know what the phase angle is. Sorry, my dog is very pissed off today, apparently. All right, so our current is given by the maximum current times the sine of the angular frequency times time. And the voltage is given by the maximum voltage times the angular frequency times time plus the phase angle. So we found all of these in the preceding parts, so we just plug them in. So our current is 0.71 amps times the sine of 160 pi radians per second times time. And our voltage is 64 volts times the sine of 160 pi radians per second times time plus 0.24 radians. All right, last chapter, electromagnetic waves. All right, so Maxwell's correction to Ampere's law states that a changing electric flux induces a magnetic field. Just like the magnetic flux had to be changing to induce an electric field, the electric flux has to be changing to induce a magnetic field. All right, an electromagnetic wave, the electric field is always perpendicular to the magnetic field. They're always at right angles to each other. And you can find the direction of propagation, the direction that the wave is actually traveling with the right-hand rule. So if you put your fingers in the direction of the electric field, curl them in the direction of the magnetic field, then the thumb of your right hand will point in the direction that the wave is traveling. All right, the pointing vector points along the direction of travel for electromagnetic wave. That part is true. It does point along the direction of travel, but it's measured in watts per meter squared. So where the pointing vector has a magnitude of the energy flux, which is the power per area. So power is measured in watts and area is measured in meters squared. All right, the radiation pressure on a perfect reflector is twice as big as it is on a perfect absorber. So you can think about this, if something is absorbing light, it gets all of the momentum that the light has, but if it reflects it, it gets all of the momentum that it has twice, right? Once for whenever it hits it, and then once more for whenever it reflects it back. All right, the intensity of electromagnetic wave is averaged energy flux. That's true. So the intensity is the average of the magnitude of the pointing vector. Now the pointing vector itself, or the energy flux, changes extremely rapidly with time. So the amount of energy or power that's being put towards some area changes so quickly. Like think the frequency of visible light is on the order of 10 to the 14 hertz. It changes so fast that nothing is able to keep up with it. So what you actually perceive is the intensity, or that averaged energy flux. All right, visible light is fundamentally different than other types of electromagnetic waves. That is not true. Visible light is just part of the spectrum. There's nothing special about it. That's just the part that we happen to evolve to be able to see. Other animals evolved to be able to see other parts of the spectrum. There's nothing special about it. All right, electromagnetic waves self-propagate because changing magnetic fields produce changing electric fields, which produce changing magnetic fields, which produce changing electric fields. That goes on forever. That's true. So electromagnetic waves don't need any help to keep going. Just the fact that they're composed of changing electric and magnetic fields sort of force them to keep going. All right, so if electromagnetic wave is traveling in the positive z direction, in what directions do the electric and magnetic fields oscillate? So this is from the right-hand rule. If you put your fingers of your right hand in the direction of the electric field and curl them in the direction of the magnetic field, then you get the direction that the wave is traveling. So if we want the wave to travel in the positive z direction, that means we put the fingers of our hand in the x direction and we curl them in the y direction. Or we could put our fingers in the negative x direction and curl them in the negative y direction, and our thumb would still be pointing in the z. That's fine, because the electric field doesn't always point along the positive x. It switches between positive and negative x, as the magnetic field switches between positive and negative y. All right, so write down expressions for the electric and magnetic fields described above. If the wavelength of the wave is 200 nanometers, and if the amplitude of the electric field is 150 newtons per coulomb. All right, so our expressions are always the maximum or the amplitude of the electric field times the cosine of the wave number times the direction that the wave is traveling in minus the angular frequency times time. Okay, so that's true for the magnetic field as well. It's always going to be the magnitude or the maximum magnetic field, or sometimes the amplitude of the magnetic field, times the cosine of the wave number times the direction the wave is traveling in minus the angular frequency times time. We actually have enough information here only knowing the wavelength and only knowing the magnitude of the electric field to determine all of those numbers. So first off, the wave number is 2 pi over the wavelength. So our wavelength was 200 nanometers. That gives us a wave number of pi times 10 to the 7, and it's measured in inverse meters. Okay. Now we also need the angular frequency, but remember the speed of light is the frequency times the wavelength. So our frequency is the speed of light divided by the wavelength. This is our 3 times 10 to the 8 divided by our wavelength, 200 nanometers. So this gives us a frequency of 1.5 times 10 to the 15 hertz. To find the angular frequency, we just multiply by 2 pi. So it's 3 pi times 10 to the 15 radians per second. Okay. And so that alone is enough to completely determine the electric field. So I put an X here because this is the X component of the electric field. We said the electric field only oscillates in the X. So the electric field has an X component, but not a Y component and not a Z component. We could also put a vector here if we put an I hat here. Okay. So we just multiply by the amplitude of the electric field times cosine of the K that we found times Z, because it's moving in the positive Z direction. If it was going in the Y direction, this would be a Y. If it was going in the X direction, this would be an X. And then we subtract the angular frequency times time. Okay. Now we do the same thing for the magnetic field. It's still cosine times all the same stuff. And we can find the amplitude of the magnetic field by dividing the amplitude of the electric field by the speed of light. Okay. So remember, the magnetic field is always suppressed by a factor of 1 over the speed of light. So it's always much, much smaller than the electric field. Here, our electric field is 150 newtons per coulomb. And the magnetic field is 5 times 10 to the minus 7 Tesla. So normally, if you have a particle that's just sitting there when the wave comes in, the electric field is going to do a lot more than the magnetic field. Okay. Last page. A long wire with current I is interrupted by a capacitor. What is the displacement current between the plates of the capacitor? Well, the displacement current by definition is epsilon naught times the derivative of the electric flux. So if we wanted to, we could calculate the electric flux given the charge on each plate here, and then take the time derivative of that and multiply by epsilon naught. But we kind of don't have to. It just has to be I, like by the symmetry in the problem. It has to be I, or from the argument that we made in class when we derived Maxwell's correction to Ampere's law in the first place. All right, so a broadcast tower releases radio waves spherically in all directions. The intensity, a distance of 100 meters from the tower, is measured to be 150 watts per meter squared. With what power are the radio waves released? Well, anytime we have spherical waves, waves that are released in all directions the same, the intensity at some point is the power that the waves are released at, or the power of the source, divided by the area of a sphere at that distance. So the area of a sphere is 4 pi r squared. So our intensity is our power divided by 4 pi r squared. We were asked for the power, so that is our intensity times 4 pi r squared. So R here is 100 meters. Our intensity is 150 watts per meter squared. And so that gives us a power of 1.9 times 10 to the 7 watts. Okay, now what are the amplitudes of the electric and magnetic fields? Well, we looked at a whole bunch of different equations for the intensity, but one of them was this. So it's the speed of light times epsilon naught times the magnitude of the electric field squared over 2. So we can solve this for the electric field. We'll get this expression. And we know the intensity, we know the speed of light, and we know epsilon naught. So the magnitude of our electric field is 336 newtons per coulomb. Now remember, the magnitude of the electric field, or the magnetic field, is always the magnitude of the electric field divided by c. And so we just divide this by the speed of light. And so we get 1.1 times 10 to the minus 6 Tesla. All right, last one. A solar sail, which is a perfect reflector, is placed some distance from an alien sun. It has an area of 1,250 meters squared. If the force on the sail is 250 newtons, what is the intensity of the light from the sun at the position of the sail? Well, the radiation pressure is given by twice I, the intensity divided by the speed of light. It's twice because it's a perfect reflector. If we had a perfect absorber instead, then this would just be 1. And if it was somewhere in between, it would be some number between 1 and 2. If it absorbed half and reflected half, it would be 1.5. All right, now pressure by definition is the force divided by the area. And so our force is this 2 times the intensity divided by the speed of light times the area. Okay, we know the force, and what we're looking for is the intensity. So if we solve this for the intensity, that tells us that the intensity is the force times the speed of light divided by twice the area. And so that gives us an intensity of 3 times 10 to the 7 watts per meter squared. And that's it.